Efficiency of the antenna is the ratio of power radiated by the antenna to the power supplied to the antenna. Antennas can be very simple dipole antennas or very complex designs like stacked Yagi-Uda antennas or Cross Yagis for LEO satellite operations. Either way, their basic function is to convert electrical signals to electromagnetic waves and vice versa, depending on whether it is used for transmission, reception or both. This is the combination 40 10-meter dipole antenna which I have mounted on a fiberglass pole. The length of the pole is 24 feet. It's on the first floor terrace. Important parameters of an antenna are the gain, directivity, radiation pattern including the angle of radiation and polarization, beam width and effective aperture. All these will determine the efficiency of the antenna for a given application. Gain of an antenna is usually mentioned in comparison with the gain of a theoretical isotropic antenna (dBi) with spherical radiation pattern all around, or sometimes in comparison with a dipole antenna (dBd). Gain of the antenna will be equal to the product of efficiency and directivity of the antenna. Directivity of the antenna is usually mentioned in terms of its front to back ratio. In other ways, how efficient the antenna is in directing the signals in one direction while cutting off radiation in other directions. High directivity will usually be associated with high gain and low beam width. Both can be useful in receiving signals and transmitting signals in one particular direction, but will be a disadvantage when you want to work stations from multiple directions. Then an antenna rotator will be needed to point the antenna in the direction of the station. For a point-to-point contact, that will be highly efficient, but if you are conducting a net, this can be a great disadvantage. Same is the case of repeaters. In both instances, we will go for an omnidirectional antenna. Omnidirectional antenna gain can be increased by having more vertically stacked elements with appropriate phasing coils in between. This is my CP22E antenna. You can see a phasing coil between the two elements. You can see that the upper element is a bit bent by wear and tear, and this has been mounted on a CPVC pipe, 3 meters of CPVC pipe, again on my first floor terrace. Dipole antennas have dumbbell shaped pattern of radiation to both sides. Radiation is much less along the ends of the dipole antennas. Hence, dipole also has some directivity along its broad side, though it is bidirectional rather than unidirectional. The bidirectional radiation pattern gives the dipole antenna a gain over the theoretical isotropic antenna of 2.15 dBi. That is why when gain is mentioned in comparison with a dipole as dBd, it will be 2.15 lower than dBi. Highly directional antennas like Yagi-Uda antennas have much more gain along the direction from reflector to director elements. Polarization of an antenna represents the orientation of its electric field. Polarization of the antenna is vertical for vertical antennas and horizontal for horizontal antennas. These can be called as linear polarization. For working LEO satellites, antennas with circular polarization is better than those with horizontal or vertical polarization. Cross Yagi is a typical antenna with circular polarization. Another antenna with circular polarization is the turnstile antenna. During construction of these antennas, if the design parameters are not followed exactly, you may end up with an antenna having elliptical polarization instead of circular polarization due to inequality of the pattern in both axes. Gain of an antenna determines how efficiently the antenna radiates electrical power delivered to it. On the receiving side, it determines how efficiently it converts electromagnetic energy received by it to electrical signals for the receiver input. Gain of the antenna is determined not only by its physical structure but also by the surrounding environment. Antenna size, elements, and the dielectric constant of the surrounding medium influence the antenna gain. Antenna height is also a very important parameter while considering the efficiency. A minimum height of more than a quarter wavelength of the operating frequency is highly desirable, though often not practical for lower bands. Lower height in relation to wavelengths tends to direct electromagnetic waves towards the sky and is often considered a wasted energy, except in case of NVIS or near vertical incidence sky wave propagation meant for medium distance contacts. Sometimes such antennas are called cloud burners in a lighter mood. Simple way of finding out how efficient your antenna is to try it out on the air, or like proof of the pudding is in the eating. But that may not always give the intended results, as it depends on band conditions and the number of operators available at that particular time to reply to your calls. You have to have some basic knowledge about which band is good at the particular time of the day and year, as well as the solar cycle. In general, higher bands perform better during daytime and lower bands better at night. Higher bands perform better when the solar activity is more, and lower bands perform better when the solar activity is lower. That is due to ionospheric reflection properties depending on the level of ionization. There are other ways to find out how your antenna works now. The reverse beacon network, or RBN, can pick up your CQ calls if sent in a machine-like precision. From the RBN stations which are picking up your signals, you can get an idea how well your signal is propagating at the given time. Of course, it will depend on the band conditions at the moment. Another option is to listen multiple web SDRs while calling CQ on the band. In radios with recording facility like FT710, you could transmit a recorded CQ call while listening simultaneously on different web SDRs. Web SDRs are software-defined radios connected to the internet, which can be tuned to different frequencies by different users simultaneously. Different types of web SDRs with varying coverage of amateur radio bands are available online. After enabling break-in, again select message after the function key, and then you have to select the message.
Hello CQ, hello CQ.
So you can see that the message is being transmitted. Antenna gain can be calculated using antenna modeling software like SNEC if the construction matches the model exactly. But it is not as easy, as parameters which have to be included in the model will include all nearby conducting structures and other antennas in the vicinity of the test antenna. If these are not properly included in the model, the gain, directivity and efficiency calculated using the modeling software will not match what you actually get in the real world. For real measurement, you need large amount of space for HF antennas and anechoic regions which will prevent echoing of the signals from nearby structures. That is not practical at the level of most amateur radio operators. This initial video clip which I had shown is enough to understand the complexity of modeling antennas in antenna softwares. You can see that different antennas are there. 40 meter dipole inverted V, 10 meter dipole, 20-meter unfed antenna, and on one side you have the CP22E antenna for VHF. What is not seen here is a Moxon Yagi, which I had shown in another video clip. All these antennas will interact with each other along with the surrounding structures of the building, electric line, electric pole, and so many things in the neighborhood.